Ladies and gentlemen, start your engines and then immediately question every design choice you just made. Mechanical engineering made simple.
Well, that is certainly a bold way to open a deep dive. But
Uh-huh.
honestly, given the source material we are unpacking today, it's pretty spot on. Questioning literally everything we think we know about, modern infrastructure is exactly what we have to do here.
Yeah, welcome everyone. I mean, if you are tuning in, we know exactly why you're here. Today's deep dive is, well, it's custom tailored for you, for your off-grid aspirations.
Right, because we know you're looking for that ultimate blueprint for real unshakable self-reliance.
Exactly. You want to know how to keep moving, keep producing, and basically survive when the modern conveniences we all just take for granted completely vanish overnight.
And to find that blueprint, it's funny, we actually have to look backward. We have to examine this forgotten era of history that, well, it feels almost like science fiction to us now.
Oh, totally.
But it was a completely unavoidable daily reality for millions of people.
Yeah, and let me just set the stage here with a premise that absolutely blew my mind when I first read our sources. Like, seriously, imagine you are in the middle of World War II, right? It's the early 1940s.
Okay, picture it.
You are standing in a field in occupied Denmark. You look around at the farm machinery, the tractors, the trucks delivering supplies, even the fishing boats. And 95% of them are not running on gasoline.
Not a drop of diesel either.
Right. 95% of that entire nation's mechanized infrastructure is running off wood, like literal chunks of wood. And, did you know that millions of cars ran off wood back then?
Millions, yeah. Or, well, gas derived from charcoal, but yes.
It is wild. And honestly, looking at this, do you also know there are like so many energy companies today that seem to be keeping this technology a secret?
Well,
I mean, think about it. I'd guess much of the gasoline industry could literally be powered by wood-burning stoves if they let us. It feels like this massive government conspiracy-style burying of information, Like they just don't want people who want to live off-grid to have this.
it's very compelling narrative, I'll give you that.
Right.
And it's a completely natural human reaction to look for, a hidden hand or a shadowy boardroom when something this useful just suddenly fades away.
Right. Because why else would it vanish?
Well, if we look strictly at the historical record and the factual reality presented in our source material today, which is a 1989 FEMA manual, the truth is actually a lot less sensational, though honestly maybe more profound.
Wait, so no corporate cover-up?
Not according to the manual. There was no secret conspiracy to bury wood gasification. It was simply human nature.
Human nature? What? People just naturally hate free fuel?
No, it's human nature to seek the path of least resistance. The manual is very explicit about this. We traded ultimate off-grid resilience for, well, convenience.
Oh, yeah. Okay, I guess that kind of makes sense.
Yeah, these gasifier units were abandoned almost immediately when liquid petroleum became widely available again around 1945, and they were abandoned for three highly documented reasons.
Which were?
The manual cites somewhat low efficiency, the sheer inconvenience of daily operation, and the potential health risks from toxic fumes.
Okay, toxic fumes definitely sounds like a deal breaker for the average commuter.
Exactly. I mean, wood gasification is incredibly hard. Physical labor. You have to physically harvest, chop, dry, and haul massive amounts of wood every day. Oil, on the other hand, is just miraculously easy.
Yeah, you just pull up, put a nozzle in a hole, and turn a key.
Right. So the technology was abandoned simply because liquid petroleum is energy dense and effortless.
Wow. Okay, so it wasn't an oil baron twisting his mustache. We just got lazy. Or, we just preferred the easy way.
We chose convenience, yeah. And this is the crucial part for you listening. When the pump runs dry, wood gasification remains the only proven scalable solution for running existing engines.
Okay, so let's talk about this manual then, because this is the holy grail for our off-grid listeners. What exactly is this document?
It is a truly fascinating piece of literature. It's an official manual published in March of 1989, prepared by the Oak Ridge National Laboratory for FEMA and the Department of Energy.
The government's absolute worst-case scenario playbook.
Basically, yes. In the archives, it's designated as OR RNL 6404.
And the title alone is it's intense. Construction of a simplified wood gas generator for fueling internal combustion engines in a petroleum emergency.
It sets a very specific stage. This was late Cold War era.
Yeah.
And the stated mission of this manual is entirely pragmatic. The authors wanted to develop detailed, accessible instructions so that any ordinary mechanic could build a wood gas generator out of everyday hardware.
Because they knew if a massive supply chain collapse happened or a war, the tractors had to keep plowing.
Exactly. If the diesel stops, the world starves. And the authors actually noted that America was way behind on this technology compared to Europe.
Right, because we never had those severe oil shortages during the war like they did.
Correct. So this manual was a deliberate attempt to preserve the practical knowledge of wood gasification before the mechanics who actually lived through it died off.
Which is why we're doing this deep dive today. We are going to break down the chemistry of how this actually works, explore the history, and then literally walk through the step-by-step construction of a wood-burning vehicle.
We are essentially going to talk about building a functioning fuel refinery out of a galvanized garbage can.
I love that so much. A garbage can refinery. Okay, before we start building, we need to talk about the physics, because this is the hurdle I think most people, myself included, stumble on.
The chemistry can seem a bit counterintuitive at first.
Yeah, like how on earth does a solid piece of wood replace liquid gasoline? How do you put a log into an engine?
Well, to understand that, we first have to clarify a massive misconception most people have about how internal combustion engines actually operate.
Oh, this part completely changed how I look at my car.
Right. Most people picture liquid gas splashing around inside the engine block and exploding.
Yeah, like a puddle of fire.
But that's entirely incorrect. Internal combustion engines do not run on liquid gasoline. They never have. They run strictly on vapor.
Okay, let me stop you right there, just so we are absolutely clear. The liquid fuel we pump into our gas tanks, the liquid we can actually see, is not what burns inside the cylinder.
Correct. The liquid fuels are vaporized. They're turned into a gas just before they enter the combustion chamber.
Even in diesel engines.
Even in diesels.
Yeah.
They operate under extreme pressure, but the liquid fuel is sprayed in as incredibly fine droplets, which instantly vaporize in the heat. They only burn as a vapor. You actually cannot ignite a puddle of liquid gasoline.
Wait, really? You can't.
No, if you hold a flame to a puddle of gas, you are not burning the liquid itself. You are igniting the invisible vapor that is off-gassing from the surface of that puddle.
That is wild. Okay, so if an engine inherently requires a gas to operate, then any solid fuel, like wood, has to be converted into a gas first.
Precisely. It must be, quote, gasified. The entire purpose of this generator unit we're building is to force that transformation, and then filter it, of course.
Right. And the manual gives this excellent analogy to explain it, the matchstick analogy.
It's a great visualization, yeah.
So if you're listening, visualize taking a standard wooden match and striking it.
And if you hold that lit match entirely still, horizontally, and look very closely at the flame, you'll notice something deeply fascinating. The wood of the matchstick turns black, it turns to charcoal.
But the wood itself isn't actually burning.
Exactly. The heat is causing the wood to release an invisible gas, and that gas begins to burn brightly a short distance away from the solid stick.
So there's actually a tiny visible gap of empty space between the black matchstick and the yellow flame.
Yes, that microscopic gap contains the wood gas. It only ignites when it travels far enough away from the wood to mix with the oxygen in the room.
So our goal with building this whole contraption isn't to make a beautiful roaring campfire inside a barrel.
No, not at all.
The goal is to capture that invisible gas in that tiny gap before it actually catches fire. We want to harvest the smoke.
Essentially, yes. Gasification is a highly controlled method of collecting that smoke. The manual defines it scientifically as a form of incomplete combustion.
Incomplete combustion, meaning we starve it of oxygen.
Exactly. The heat forces the wood to release gases, but because there isn't enough oxygen present, those gases are physically unable to burn completely.
Okay, so we're trapping this unburned smoke. What actually is this wood gas, chemically speaking?
By weight, the gas produced in a properly functioning unit contains 3 primary combustible elements. It is roughly 20% hydrogen gas, roughly 20% carbon monoxide, and trace amounts of methane.
Wait, hold on. Carbon monoxide, the intensely poisonous stuff, the stuff we have detectors for in our homes because it can kill you in your sleep, we are using that to power a car.
We are. Carbon monoxide is highly combustible. It's a foundational component of wood gas. When it burns, it combines with oxygen to become carbon dioxide, releasing heat energy.
Okay, that is just crazy to think about. But wait, if I do the math there, 20% hydrogen, 20% carbon monoxide, a little methane, that's only like 40-something% of the total gas volume.
Right.
What's the rest of it?
And here is the major catch. This is the primary limitation of the whole technology. Between 50 and 60% of the volume of wood gas is just nitrogen.
Nitrogen, like the incredibly common, completely inert nitrogen that makes up our atmosphere.
Exactly that. It gets drawn into the system from the outside air, and it passes straight through the gasifier, completely unchanged. It's non-combustible. It does absolutely nothing to power the engine.
But it takes up space.
A lot of space. It severely dilutes the combustible wood gas as it enters the engine cylinder.
Ah, okay. It's a density issue. Like, if you have a 1-liter cylinder and you fill it with gasoline vapor, almost all of that vapor is ready to explode aggressively. But if you fill that same cylinder with wood gas, over half of it is just useless nitrogen. It's like trying to pack uncompressed cotton candy into a suitcase when you really need dense, hard candy. You fill up the whole suitcase, but there's no actual substance.
That is an excellent way to visualize it. The nitrogen takes up critical space, meaning less fuel and less oxygen can fit inside before the piston compresses.
So you get a much weaker explosion.
Exactly. This explains the somewhat low efficiency the manual warned about. A vehicle running on wood gas will typically experience a 30 to 50% loss of maximum horsepower.
50%. That is a massive hit. Your truck is going to be incredibly slow.
It will struggle up hills, yes. But remember the context. The goal isn't high performance. You're not trying to win a drag race.
True.
The goal is raw survival. A slow tractor plowing a field on wood gas is infinitely more useful than a fast tractor sitting dead because there's no diesel.
Fair point. I'd rather have a slow truck than a giant metal paperweight.
Okay.
So we're starving a fire of oxygen, forcing incomplete combustion, and trapping this diluted gas.
Yes, but understanding the chemistry is the easy part. The mechanical engineering, how to actually do this safely and efficiently, while bouncing down a dirt road, that is the real challenge.
Which perfectly sets up the evolution of the machine itself. Let's look at how the design changed. Because if millions of these were used in WWII, why does this 1989 manual propose a totally new design?
Well, to understand the new design, we have to understand the severe flaws of the old one. The manual spends time analyzing the classic World War II era Imbert gasifier.
Imbert, named after a French inventor, right?
Yes, Jacques Imbert. This was the gold standard in the 1940s.
Okay, walk us through the Imbert model. What did it look like?
Physically, it was a tall cylindrical metal tower. The upper portion was a large fuel hopper where you loaded the wood. But the critical design feature of almost all early gasifiers was that both the hopper at the top and the combustion unit at the bottom had to be absolutely perfectly airtight.
Airtight. So the hopper where you put the wood had a heavy sealed lid.
A heavy, spring-loaded, airtight steel cover, secured with latches. And this requirement caused major daily operational challenges.
Because you have to open it to put wood in.
Exactly. Every time you ran low on fuel, you had to physically open this completely sealed environment.
And based on the chemistry we just discussed, that environment is full of hot, highly toxic carbon monoxide gas.
Yes, and because the internal pressure was often slightly positive, a thick plume of raw, toxic smoke vented directly into the air and often directly into the operator's face the moment that lid was cracked open.
Getting a massive face blast of toxic gas just because you need to refuel your tractor does not sound sustainable.
It was a huge health hazard. But the toxic face blasts weren't even the primary mechanical flaw. The real problem was a feature called the constricted hearth.
The constricted hearth. Okay, break that down. What does that look like inside?
About a third of the way up from the bottom, the physical metal walls of the gasifier narrowed dramatically, creating a strict funnel shape, or a constriction.
Why would they intentionally constrict the flow? Don't you want the wood to just fall down smoothly?
It was a chemical necessity for them. When wood heats up, it releases heavy, sticky, complex hydrocarbons known as tars.
And tars are bad for engines, I'm assuming.
Oh, fatal. If tars get into an engine, they coat the valves, cool down, harden like glue, and completely seize the engine block.
Yikes.
Okay? So by forcing all the air and the falling wood through a very narrow, violently hot funnel, it ensured those complex tars were thermally shattered and broken down into simpler, harmless gases.
Conceptually, that sounds smart. It forces the dirty smoke through the hottest part of the fire to clean it. What's the downside?
The physical, unpredictable nature of raw wood. Because of that severe funnel, the Imbert gasifier was incredibly picky about its fuel. It required perfectly uniform, blocky chunks of wood.
So you couldn't just throw in random branches or twigs?
Absolutely not. The manual describes a phenomenon called bridging and channeling. If you put irregular shapes in there, long twigs, stringy bark, they fall down and inevitably jam up against each other at that narrow funnel opening.
They form a physical bridge across the gap, like rocks jamming in a pipe.
Exactly. And once a bridge forms, fuel stops flowing down. The fire below burns out the remaining charcoal, creating an empty pocket.
Oh, I see where this is going.
Right, and then suddenly, the bridge collapses. Raw, unpyrolized, tar-heavy wood falls directly into the lower zone, ruining the gas quality and sending a lethal dose of tar straight towards your engine.
That sounds like an absolute engineering nightmare.
It was. During World War II, entire massive industries emerged just to mill perfectly sized, identical wood blocks for these vehicles. You couldn't just chop down a tree. You needed uniform cubes.
That defeats the whole purpose for an off-grid scenario today. If I'm trying to survive a crisis, I don't want a machine that requires a specialized sawmill. I want a machine that eats whatever rough scrap wood I can find.
Precisely. Which brings us to the breakthrough, the modern solution, the stratified downdraft revolution.
Yes. Developed by this massive scientific brain trust in the 80s, right?
Yes, researchers from the Solar Energy Research Institute, UC Davis, the Biomass Energy Foundation, a lot of brilliant minds focused entirely on burning wood in a barrel.
And what was their massive breakthrough?
They developed stratified downdraft gasification, also known as open-top gasification.
Open top.
Yes, they completely eliminated the need for the sealed, airtight fuel hopper at the top.
Okay, I have to push back hard on this. That sounds like it violates everything you just said about starving the fire of oxygen. If the top of the barrel is wide open, won't it just burn up like a normal crash can fire?
It is deeply counterintuitive, I agree.
And also, heat rises, fire goes up. How does an open top not just result in a massive pillar of toxic smoke pouring out into the sky?
This is where the brilliant application of physics comes in. The new design relies entirely on a balanced negative pressure concept driven by the engine itself.
Negative pressure, so suction, like a vacuum cleaner.
Exactly like a vacuum. When the piston moves downward inside the engine cylinder, it creates a powerful suction force. In this system, that suction is piped directly to the very bottom of the gasifier unit.
Oh.
So this powerful vacuum pulls atmospheric air downward into the open top, violently dragging it through the raw wood, through the fire, and pulling the gases out the bottom.
Wow. So because the engine is constantly pulling air downward, the smoke literally cannot rise up and escape out the top. The suction overpowers the natural heat rising.
Correct. The inward rush of air acts as an invisible lid. And because this design uses a simple straight-walled cylinder without any of those severe inverted funnels, it allows for a smooth flow of fuel.
So bridging isn't an issue anymore because there's no bottleneck.
Exactly. You can throw in blocky fuel, rough chips, jagged branches, whatever is available. It makes the unit incredibly forgiving.
Okay, so let's look inside this open-top cylinder while it's running. The manual breaks the inside down into 4 specific distinct zones, right? Like layers of a volcano.
Yes, hence the term stratified. As the fuel moves downward by gravity and the air is pulled downward by suction, they pass through 4 distinct zones.
Let's walk through these in detail. Zone 1 at the very top.
Zone 1 is the uppermost region. It contains the unreacted fuel. Just the fresh, raw wood chips you dumped into the open top. This is where the air enters.
Simple enough. Just wood waiting its turn. Moving down to Zone 2.
Zone 2 is the pyrolysis zone.
Pyrolysis. Let's break that down for the audience. What does that actually mean?
Pyrolysis is the thermal decomposition of organic material at elevated temperatures in the absence of sufficient oxygen.
So the wood gets so hot it starts breaking apart chemically rather than just burning?
Correct. It releases water vapor, heavy tars, and volatile gases. And in the lower portion of Zone 2, some of that incoming oxygen finally reacts with these gases, burning them fiercely.
Okay, so that localized burning provides the intense heat needed to keep cooking the fresh wood above it.
Exactly, it feeds on itself. And crucially, the fire in Zone 2 burns up absolutely all of the free oxygen that was pulled in from the top.
So when everything moves downward into Zone 3, there's no free oxygen left.
Precisely. And that is where the most critical chemical conversion happens. Zone 3 is a deep, glowing bed of pure, extremely hot charcoal left over from Zone 2.
Okay, a bed of glowing charcoal, but no oxygen. What happens?
As the extremely hot combustion gases from Zone 2, which are mostly carbon dioxide and water vapor, now are pulled through this oxygen-starved charcoal bed, a chemical process called reduction occurs.
Reduction. Okay, let me try an analogy for this because this is where the magic happens.
Go for it.
Imagine the glowing carbon atoms in the charcoal are incredibly desperate for oxygen, but there's none left. Then a carbon dioxide molecule, CO2, floats by. It has 2 oxygen atoms. The glowing charcoal acts like a ruthless toll booth. It says you cannot pass unless you pay a toll of 1 oxygen atom.
I like this.
The charcoal literally rips an oxygen atom off the CO2. The CO2 loses an oxygen and becomes CO carbon monoxide, and the charcoal atom that stole the oxygen also becomes carbon monoxide. Is that essentially it?
That is an exceptionally vivid and accurate description. The glowing solid carbon physically strips oxygen atoms away from the passing gases. It does the same to the water vapor, forming carbon monoxide and leaving behind free hydrogen gas.
That is brilliant. It reverse engineers the exhaust back into fuel. And finally, zone 4 at the bottom.
Zone 4 is inert char and fine ash. It's depleted of energy, but it acts as a thermal buffer and protects the metal grate from the extreme melting temperatures of Zone 3 right above it.
It's just a beautifully elegant chemical symphony, which makes the next part so incredibly funny to me.
The fabrication.
Yes, we have this precise stratified chemical process, and the manual tells us to literally build it out of an old garbage can.
It is the absolute pinnacle of pragmatic survivalist engineering, the MacGyver blueprint.
I mean, the materials list doesn't read like a high-tech lab requisition. It reads like a weekend scavenging trip to a junkyard.
The authors were very intentional about this. They noted that the exterior shape and materials have little effect on the chemistry. The fire doesn't care what kind of metal is holding it.
So what are we actually starting with in our garage?
The primary prototype consists of a standard galvanized metal garbage can placed securely atop a small metal drum or barrel, connected with common plumbing fittings.
A garbage can hopper. But the part that killed me, the single craziest design choice in the entire manual, is the internal grate.
Yes,
The grate has to hold up the 1,000-degree glowing charcoal, but let the ash fall through. What did these highly credentialed government engineers specify for this?
a large, standard stainless steel kitchen mixing bowl.
A kitchenware mixing bowl? Like for potato salad. How does that work as an industrial grate?
The builder drills a series of specific holes into the bottom of the bowl, large enough for fine ash to pass, small enough to hold the charcoal. Then you attach metal chains to the lip of the bowl and hang the entire assembly inside the lower drum using U-bolts.
Wait, why is the bowl hanging on chains? Why not bolt it solidly to the drum?
Ash removal. As the charcoal breaks down, it turns into fine dust. If this dust isn't continuously removed, it plugs the downward airflow, choking the engine and causing severe overheating. The ash must be constantly agitated.
Ah, and the prototype is mounted on a farm tractor.
Right. The natural motion and vibration of the tractor driving over rough ground shakes the suspended bowl automatically, sifting the ash without human intervention.
That is so clever. Let the potholes do the maintenance. But what if I'm using this for a stationary electrical generator at my cabin? There are no bumps to shake the bowl.
For stationary engines, the design includes a hand-operated shaker mechanism. You fabricate an external lever that connects to the grate. The operator just manually grabs the lever and violently shakes the bowl every few minutes.
Shake the bowl, save the world. Now, while they are very loose with using mixing bowls, there is one non-negotiable rule the manual insists on.
Absolute flawless airtightness below the combustion zone.
Clarify that. We just said the top of the garbage can is wide open. Why is airtightness suddenly an issue?
Everything below that primary fire, the lower drum, the ash cleanout, the plumbing, must be perfectly sealed. If a structural air leak develops, say a bad weld, the powerful vacuum created by the engine will instantly suck fresh, oxygen-rich air directly into that 1,000-degree gas-filled environment.
Oh no. So the hot explosive gas suddenly gets oxygen.
Precisely. It will immediately ignite and burn ferociously inside the lower drum and plumbing.
You've accidentally built a literal blast furnace in your plumbing.
It is a catastrophic failure. It will melt the thin metal housing. So
Wow.
high-temperature silicone sealant and Teflon tape are absolutely essential for every single joint.
Duct tape won't cut it. Got it. Okay, so we've built the gasifier. It's sealed. Can I just run a pipe straight from the garbage can into my engine block?
If your goal is to completely and irreversibly destroy your engine, yes.
Let's avoid that. So we move to cooling, filtering, and carburation. The gas exiting the drum is roughly 1,000 degrees, full of ash dust. What do we do?
First, address the extreme temperature. It must be heavily cooled.
Why? Engines are designed to get hot.
It's a density problem. As gas heats up, it expands, its density decreases.
Then the fluffy cotton candy again. Takes up space, but no actual fuel molecules.
Exactly. The manual provides a metric. The ideal target temperature at the manifold is 70 degrees Fahrenheit. For every 10 degrees the gas rises above 70, you lose an estimated 1% of your horsepower.
That's a staggering penalty. So if it hits the engine at 170 degrees, you've lost 10% of your total power just from heat expansion.
Correct. So for stationary or slow-moving vehicles, a highly efficient gas cooler must be placed into the plumbing.
And what about the ash and dust? Microscopic grit in the engine sounds bad.
It's fatal. It acts like grinding paste. The system requires a robust primary filter.
And what high-tech filtration media do we use in our post-apocalyptic setup?
Common wood chips.
You use wood chips to filter the toxic dust out of the wood gas that you made by burning wood chips. That is beautifully circular.
It is highly practical. The hot gas flows up through a packed bed of small wood chips, trapping the soot. When they get clogged, you just dump them into the gasifier as fuel and put fresh chips in the filter.
Zero waste. Okay, the gas is cool and clean. Now we have to get it to burn. But we establish it's starved of oxygen. It can't burn on its own. We have to mix it with normal air before it hits the spark plugs.
Yes, carburation. Ideally, it should be mixed in a ratio of 1:1, air to gas, by volume.
But I'm guessing we can't use a standard carburetor for this.
No, standard carburetors atomize liquid fuel. They are useless for mixing two gases. The manual details building a custom dual-valve unit using homemade butterfly valves.
Homemade butterfly valves. So basically a flat metal disc on a rotating rod inside a pipe. You turn it flat to block flow, turn it sideways to let gas pass.
Exactly. You fabricate two of these. One controls the wood gas volume, the other controls fresh atmospheric air, and they must be linked mechanically so they're continuously adjustable from the driver's seat.
So you're driving down the road, and instead of just pressing a gas pedal, you are actively adjusting the air-fuel mixture by hand with levers in real time, like a WWII fighter pilot tweaking fuel mixtures on the fly.
It requires an active operator, yes.
Are there internal engine modifications needed?
Two simple ones. First, spark plug gaps should be adjusted very tight between 0.012 and 0.015 inches.
Most modern plugs are much wider. Why so tight?
Wood gas is significantly harder to ignite. The high nitrogen content makes it dense with inert material. A tighter gap ensures a hotter, more concentrated spark arc.
Makes sense. And the second adjustment?
Ignition timing must be mechanically advanced.
Advanced timing, so firing the spark plug earlier in the piston's upward stroke? Why?
Wood gas burns more slowly than gasoline vapor. By advancing the timing, you give the slower burning gas the extra milliseconds it needs to fully expand and reach maximum pressure exactly when the piston begins its downward power stroke.
Giving the slow explosion a head start. Perfect. Okay, our MacGyver machine is plumbed, cooled, filtered, timed. Let's talk about the gritty reality of daily off-grid operation. How much wood are we actually chopping and hauling?
The fuel economics highlight the physical labor involved. It takes approximately 20 pounds of wood to equal the chemical energy of 1 single gallon of gasoline.
20 pounds for 1 gallon? That's an incredible amount of weight to carry around.
It's exceptionally bulky. 1 cubic yard of chopped wood produces only 500 to 600 pounds of usable fuel. You sacrifice a lot of cargo space.
And does this open-top design still need perfectly dry wood like the old invert ones? Can I just throw green branches in?
It absolutely requires dry wood. Water is the enemy of combustion. It must be brought down below 20% moisture by weight.
How does a DIY builder out in the woods know if it's below 20%?
The manual provides a low-tech solution, the kitchen oven test.
We're going to bake the wood.
Yes. You weigh a small specimen of your wood, record the initial weight, and place it in a kitchen oven at 220 degrees Fahrenheit for 30 minutes. You reweigh it, reheat it, and repeat until the weight completely stops decreasing.
That final weight is the absolute dry weight.
Right. And the weight lost is the water content.
Baking pine next to the Sunday roast to calculate fuel mileage. Amazing. All right, we have our dry wood. Walk us through the startup sequence, because I assume you don't just turn the key.
It is a highly deliberate process. First, before anything, you must aggressively agitate the grate shaker for at least 20 seconds to clear out the accumulated fine ash.
Clear the machine's lungs.
Then, open the lower ash port, physically scoop out the ashes, lubricate the threads with silicone sealant, and close it incredibly tightly with a wrench to ensure that life-saving airtight seal.
Check. What goes in the top?
Fill the fire tube with high-quality charcoal roughly 4 inches above the mixing bowl grate. Then fill the hopper above that with your prepared wood chunks. Adjust the top lid, but leave a 3/4 inch clearance gap for the massive air intake.
Loaded and primed. How do we light it? Drop a match in the top.
No, if you drop a match in the top, the fire burns upward. We need to artificially establish the downdraft section first. You close the carburetor air valve to isolate the engine and start a separate external blower mechanism.
A blower?
Yes, a small blower to create the initial vacuum downward through the fire tube. You run this for a full 30 seconds before introducing any flame.
Why 30 seconds?
A critical safety step to purge the entire plumbing system. It vents any explosive residual wood gas left from the last time you ran it. If you don't purge it, lighting the fire could cause a violent explosion inside the drum.
Don't blow up the garbage can. Got it. System is purged. Now what?
With the blower still running, Open a small ignition port near the bottom. Take a crumpled piece of newspaper, light it, and using a long stick, physically shove the burning paper directly into the charcoal bed through the port.
Shoving flaming newspaper in with a stick, wonderfully rudimentary.
Once thick smoke appears at the blower exhaust, indicating the gasification process has begun, quickly seal the ignition port tightly. When the gas quality is good, usually determined by daringly holding a flame to the exhaust to see if it sustains a strong blue flame, you flip the valves, jump in the driver's seat, and turn the ignition key to start the engine.
That is an absolutely incredible morning routine. But as dirty as that is, we need to talk about the lethal threat lurking in this machine, because this is a matter of life and death.
Yes, I want to take a very sober tone here. The manual dedicates an entire section to this. Anyone attempting this must understand the severe risk.
Carbon monoxide, it's 20% of the fuel.
Intensely poisonous,
Yeah.
odorless, colorless. The single major hazard of everyday operation is fatal carbon monoxide poisoning.
But if the plumbing is perfectly sealed and the engine is sucking the gas, where is the danger to the driver?
The greatest acute danger occurs immediately after you turn the engine off.
Oh,
When you shut down the vehicle, the engine instantly stops creating suction. It stops consuming gas. However, the deep bed of charcoal inside the unit is still well over 1,000 degrees.
right. It doesn't just instantly go out like a light bulb.
The pyrolysis and chemical reduction continue vigorously on their own heat. The gasifier keeps making gas. But without the engine vacuum pulling it away, massive pressure rapidly builds up inside the sealed unit for approximately 20 minutes as the embers cool.
So for 20 minutes, this drum is silently manufacturing highly pressurized poison gas. It will inevitably vent out of the open top or force its way through imperfect seals.
Precisely. And the gas formed during this cooling period is extremely concentrated, 23 to 27% carbon monoxide, lethally toxic in enclosed spaces.
So let me emphasize this for anyone listening. You can never, under any circumstances, pull your wood gas vehicle into an enclosed garage, shut the door, and turn off the engine.
The manual explicitly states it must cool completely outdoors in a well-ventilated area for at least 20 minutes. It also strongly advises against the operator staying inside the enclosed cab during this time, just in case gas vents forward.
It requires a completely different psychological mindset. You are actively managing a volatile, toxic chemical reaction that takes a long time to go to sleep. You have to respect the chemistry.
It demands constant vigilance. Which brings us full circle to why this was universally abandoned. It wasn't a shadowy conspiracy suppressing free energy. It was the universal human desire to avoid mortal danger, daily mess, and exhausting physical labor.
And that leaves us to our summary of this mind-expanding journey. With nothing more than common hardware parts, a garbage can, a small metal drum, plumbing fittings, and a kitchen mixing bowl, combined with an understanding of pyrolysis and chemical reduction, you can bypass the multi-trillion-dollar global petroleum supply chain.
You can achieve undeniable self-reliance, utilizing a proven technology that literally saved entire nations from mass starvation during the darkest days of World War II.
But we want to leave you with a final philosophical question to ponder. We collectively abandoned wood gasification because of its inherent inconvenience. We traded the daily labor of chopping wood, the dirt, the very real danger of carbon monoxide poisoning, all for the effortless turn of a key at the gas pump. We chose easy over hard.
But in making that trade, we inextricably tied our personal survival, our agricultural output, and our entire global logistics network to a highly fragile liquid fuel supply chain. We optimized for ease, not decentralized resilience.
So is our modern convenience actually our greatest vulnerability? Because if a crisis comes and the pumps run dry, the person who knows how to turn a garbage can and a potato salad mixing bowl into a functioning fuel refinery will be the one who keeps moving.
True resilience rarely looks sleek. It looks like hard, dirty work and a deep understanding of basic physics.
So the next time you look at the trees outside your window, don't just see nature. Look closer. See your future. Completely off-grid fuel station. Because when the normal systems fail, you'll need to know how to start your engines and question every design choice you just made. Thanks for joining us on this deep dive into the lost art of wood gasification. Stay curious, stay resilient, and we'll see you next time.